All right, in these next few lectures, we want to look at optimization problems. So these are just max-min problems that are word problems. So we know how to find the maximum and minimum local, global, whatever of a curve, right? So if I give you a function, you know you can take the first derivative, find the critical points, and then see if that thing is a local max or a local min or global. So here we just want to do that with word problems, right? And so the hard part is to really just translate the information, right? Translate the word problem into a function that you can differentiate, right? So here's sort of the typical introductory example, right? It's a farmer wants to enclose a rectangular field along a river, and so we've got a fixed amount of fencing that we can use, right? And so we want to find the field that we can enclose of the largest area. So in particular, right, here's how the problem reads. A farmer has 400 feet of fencing to enclose a rectangular corral that borders a river. If no fencing is required along the river, what is the largest area that can be enclosed, right? What's the largest area of this field? So we want to look at, first thing we want to do is draw a picture, right? Label the thing with some variables and then try to get a function out of it. Usually these problems, there will be two equations that you'll have to put together. One of them is the objective. That's the thing that you want to maximize or minimize, and the other one is the constraint. So let's have a look at those two things now. Okay, so we want to find this field of maximum area. Here's a rough sketch of what this situation, what this system looks like, right? So we've got a river, and we know the field is going to border this river. And so now we've got three sides that we need to run fence along, right? So because this thing is a rectangle, whatever I call this side, I need to call this side the same thing. So let me call this side X. That means I have to call this side X. And then I'll just call this side something different. We'll call it Y, right? So that's a basic rectangle. And so what do we know about these three things, right? How can we relate or these two quantities together? Well, I know I've got 400 feet of fencing, so I know that 2x plus y is going to be equal to 400. This is our constraint equation. And so we'll say what we did off here in a minute. What's the thing that we want to maximize or minimize? Well, we want to maximize area in this case. And so we know that area is just x times y. So that's going to be the area of this field. The problem here is that area is expressed in terms of two variables. We know how to maximize and minimize things in one variable. So the thing to do here is to write area as a function of just one of these two variables. So that's what I did here. I'm going to solve for y, right? Solve for the variable y in terms of x. And so now I can replace y with 400 minus 2x, right? So just solve this thing for y here. And now replace this y with 400 minus 2x. So now area as a function of x, right? So area expressed as a function of the single variable x is just, right, x times y, which is 400 minus 2x. So if you want, so we don't have to use the product rule, I'm just going to distribute. So a of x now, right, the area function is just 400x minus 2x squared. And so it'd be helpful, remember we've got the extreme values theorem that says we can always find a maximum or a minimum whenever we're on a closed bounded interval. So in this case, we are definitely on a closed bounded interval, right? If x is 0, so now picture what happens to this field if x is 0. All we've got is just sort of a line that's given by y. And so if x is 0, then y is going to be 400. Anyway, that's one end of the domain, right? X can be 0. Well, what's the other extreme sort of that x can be, right? What if y happens to be 0? Well, if y is 0, right, if y is 0, you can see here that x then has to be 200, right? So if y is 0, then if we've got 400 feet of fencing, then we've got 200 here and then 200 going back in the other direction. So we want to maximize this function on this closed bounded interval. Make sure you're good on why the closed bounded interval is from 0 to 200 in this case. And not all of the problems that we will look at will have a closed bounded interval. But in this case, we do. And maybe we'll look at one more example where we have to find this closed bounded interval. So the only thing left to do now is to find a critical point of this thing, or critical points, and then plug that critical point into the original function, and then plug the endpoints into the original function, and then see which one is the highest and which one is the lowest. We've done the hard part. The easy part is to take a derivative, set it equal to 0, so we can find the critical point, and then plug in a few numbers to see what's the max and what's the min anyway. So remember, our area function is 400x minus 2x squared. We're on the closed bounded interval from 0 to 200. The derivative is 400 minus 4x, right? So just a regular old derivative of a polynomial. So when is that thing equal to 0? Well, just by inspection, you can sort of see, or you can do a little algebra either way. You can see that x must be 100. So this is the x value, or the x dimension, if you like, that will give us the maximum area. So, well, we need to check this critical point and the endpoint. So let's do that now. So when I plug 0 into the original area function, I'm certainly going to get 0, right? 0, and there's a 0 here, so I'm just going to get 0. When I plug in 100 into the original, I get 400 times 100 minus 2 times 100 squared. So this is 40,000, and this is 20,000. And so when I subtract, I'm just going to get 20,000, which is positive. And then when I plug in 200, here I'm going to get, right, sorry, this is a 200. Right here I'm going to get 80,000. And then 200 squared is 40,000 times 2. So again, that's 80,000. So here I get 0 again. So we're guaranteed that at x equals 100, we get an absolute maximum. And what is the absolute maximum value? What is the absolute maximum area that we were looking for? Well, that's 20,000. So this question could have been phrased a couple ways, right? Find the dimensions of the field that give the maximum area, or find the maximum area. Let's go ahead and write it all down. So this is the x-coordinate that will give me the maximum area. And remember, 2x plus y is equal to 400. So if x is equal to 100, that means y must be equal to 200. So x is 100, y is equal to 200. So these are the dimensions that will give me the maximum area. So if this thing is 100 and this thing is 200, then I'm guaranteed to have enclosed the maximum area. And then what is the maximum area? So the maximum area in this case is 20,000 square whatever, right? So I think the way we ask the question, right, what is the maximum area that we can enclose, that would be this thing. What are the dimensions of the field that will give the maximum area? That would be this thing.